This is a production of Cornell University.
Okay, thanks, Jacob, and sorry for the mouthful of a title. I shortened it a little bit for here, but oh well. Okay, so building off of what Evan said about cassava already, I'll just jump right in. Some of the major cassava breeding targets that the programs in the Next Gen group work on are pest and disease resistance. Sorry about the I need to figure out how to hold this better. Okay, including CBSD or cassava brown streak disease. This is the root on the left, and then cassava mosaic virus, which is the mosaicing on the leaf here. Yield and field performance, so the number of roots per plant, the size of the roots is shown here, and then quality traits. And these are all part of the selection indices that are used by the breeding programs. Today, I'm going to focus mostly on this quality trait part, and the actual measurement that's put into the selection index is the root dry matter content. This is the percent of the root that's not water, and that's calculated by the dry weight over the fresh weight times 100%. It's a major component of the dry yield and the food quality, so it factors in to needs of both processors, farmers, and consumers. It's typically ranges from 20 to 45%, with the higher the better. The 20% is not something you'd actually want to eat or grow. And it's not uniform within the root, which is something I'll come back to later. The dry matter content's mostly made up of starches and carbohydrates, with some protein, fiber, ash, lipids as well. So though it's really important for breeding programs, it's time consuming and laborious to measure. So in Uganda, the roots are graded by hand. They're dried in big ovens. And when you consider that there could be thousands of plots per breeding program per season and limited electricity that could make the ovens go offline, and then off-site trials that you have to transport the roots back and forth, that creates a lot of work. So the goal is to reduce the amount of work that breeding programs have to do each season. And that's where near-infrared spectroscopy comes in. And this has been used before in cassava, but I'll explain a little bit about what it is. So this is looking at the reflectance in the near-infrared region of the electromagnetic spectrum. This is 780 to 2500 nanometers, so just beyond the visible. It's measured by using an active light source that emits wavelengths in this range on a biological sample, and then the sample itself changes the reflectance pattern that's sensed by a sensor. And so this is what cassava looks like when you scan it with a near-infrared spectrometer. So we see reflectance on the y-axis and wavelengths on the x. And this tells us about the chemical and physical properties of the sample that was scanned, but the signal that comes back is complex. And so it requires multivariate statistical techniques to decipher what's actually going on. But once you have models calibrated for the traits of interest, you can measure these traits quickly and non-destructively. So like I said, it's been used before in cassava to look at dry matter content in roots. This has been done, first of all, with the FOSS 6500. This is a benchtop model that's been shown to be highly predictive of dry matter content, so above 0.94 in the literature. And then we have a spectral range here that includes some of the visible range as well, from 400 to 2500 nanometers. The next generation was from Ugo Ikeogu from Jean-Luc's lab. And he looked at this mobile spectrometer, the quality SpecTrek. It has an even larger spectral range, but the predictive ability dropped a little bit in his test to 0.8, which is still pretty good. And it passed the standards for breeders. But the problem with these two units is they're really expensive. And for a small breeding program, this might be way out of the budget. You could fund extra workers, you could put extra field plots, do more trials for this amount of money. So for these reasons, we've been looking into the SCIO, which is a small handheld spectrometer that's only $300 per unit. But it does have a smaller spectral range, and this means that we need to evaluate the performance of the spectrometer before we can fully recommend it to breeding programs. In order to do that, we collect calibration data, so scans from the spectrometer paired with these oven measurements that I was talking about before. We use those as input for prediction model development, and once we have models that pass our standards, we can use them routinely in breeding programs. But to get to that point, we need to optimize the protocols that we're using, both in actual sampling of the roots and in model development. And then we do need to keep going back and making sure that our models are still appropriate as our populations change and we have new generations. So the calibration data collection looks like selecting several roots per plot and then slicing them. So this, we have 3 different slice points, and that is so that we can cover the variation within the root. These root slices are each scanned with the spectrometer, and then we take a mean plot dry matter content measurement using the oven method that I talked about earlier. And these scans are paired with these measurements, and those go into our prediction models. So these are the populations that I've been working with so far. The dry matter content varies pretty widely, both within and among both trials and breeding programs. I want to point out a couple things here. First is these 2 trials at Embrapa in Brazil are seedling evaluation trials. And if you talk to any cassava breeder, you'll know that seedling evaluation trials from true seed are not always indicative of what the plant will actually do when you take a clonal propagule from it. So we see a wide range of dry matter content in those 2. These 2 trials from IITA are actually the same genotypes grown in 2 different years. So we do see a lot of variation due to environment here. And then this trial at NACRI has a low tail here for dry matter content. And that is because of CBSD incidents in Uganda. So that's those disease roots from that first slide that I showed, and that really affects the dry matter content of the plots. Okay, so once we have these oven dry matter content measurements paired with our scans, we can use those to create prediction models. So I divide them into training and test sets, and then use 5-fold cross-validation and to tune partially squares model parameters with the training set, and then use the optimized model to predict our test set. I output model performance statistics like R squared, root mean squared error, and then I repeat this with different subsets of training and test sets. So when we look at performance within breeding programs, so that's the diagonal. This is not a correlation matrix. It is a training set on the y-axis, test set on the x. This is whole breeding program performance. So we can see up in the top left is using IITA data to predict IITA data, and then so on. So this is in 2018. We see that model performance is pretty high. We got 0.85 R squared with a 2.6 RMSE for IITA, and then going down there. But the real test would be to see how the models perform when you're training on one breeding program and testing another. So can we train models at IITA and test them in Rwanda, say? Answer is mixed bag. We have some models doing really well, like using the Embrapa data to predict the plots at NACRI. But then when you use IITA, we're getting poor performance predicting either of the other breeding programs. This is a little concerning, but again, we could just train models for each individual breeding program. Ideally, though, we would use everything we have and train like a major model and then use that to test everything. And so when we do that, we actually see the performance go back up, which is pretty great. So this is really comparable to this diagonal here. We only lose very small amount of our predictive ability. But in order to make these big models using everything we have to be able to put everything together in one place. So this is where Cassavabase comes in. I've been working with Lucas Mueller's group to create the infrastructure to store and access spectral data within Cassavabase. And this will allow for us to take training and test sets from any trial within the database and then use them to build and evaluate models. So the functions that I've been writing and using for my own work, we're putting into Cassavabase for use by any breeder. And then they can build, evaluate their own models and use them for prediction. And then the predicted values can be used for selection in those selection indices that I've been talking about. So that's our plan moving forward, but I'd really like to thank all of the next-gen Cassava breeding programs, the Gore Lab, the PhenoApps team, my committee, and then the funding from the PhenoApps project. So with that, I'll take questions. Yeah, Evan?
Back when you're testing, which is the train, what is the test set?
Mm-hmm.
Have you looked at like the whole one holdout, like you can buy two of them and see how long they can just combine two of them help that, or is it perfect for battery?
So by combining two, you mean two programs, or?
You train one big model with all three of them at the end, right?
Mm-hmm.
But I just wonder if there's like a test set that isn't in the big model. Does that make sense?
Yeah, so here what I did is train on two programs and like 70% of the third and then test on that 30% holdout. So I haven't tried training a model on, say, IITA and NACRI and predicting MBRAPA, but that's definitely something that I could do. Mm-hmm. Thanks. Yeah, Ed?
When you do this training here, does it know, does your model get to see which environment they came from, or do you only show it the spectrum?
So for here, I'm just training it on the spectra, but I do have test plots from all of the environments included in the training set. So I also have done cross-validation schemes that hold out an entire environment or specific genotypes. And those, as you'd expect, perform a little more poorly than these do.
But that looks really nice.
Yeah, it is pretty exciting. Chantal.
Do you get the data from previous studies like those work to help look at the data and how it compares? I mean, it was looking at a wider range of devices, because it's a much smaller window. But you look at that data set and that small window,
Yeah, so the question was, could I subset the data from the spectrometers with a larger range to my smaller range and compare how they do compared to this one? Yes, we actually did that before starting with Ugo's data, is take a subset from 740 to 1070 nanometers, which is the SCIO's range, and saw pretty high performance. I don't remember the exact numbers off the top of my head, but in the high 0.8s, for dry matter content. We also looked at carotenoid content for that and saw it was, as expected, pretty low because most of the signal for carotenoids is in the visible range, which is outside the range of the SCIO. So that's why we went ahead and moved forward with the dry matter content. Yeah, thank you.
Are there any questions over Zoom? Okay, well, thank you very much, Jenna.
Thank you.
This has been a production of Cornell University, on the web at cornell.edu.